Welcome to this video. So it's called Ocean Turbulence and Models. I'm François Schmidt. I'm research professor at CNRS, and this works is supported by the graduate school IFSI, meaning Graduate School for Marine, Fisheries and Seafood Sciences. This is belonging to a series of 7 short videos, and this is the third one about turbulence modeling. So in fact, we have 3 approaches in geosciences. We have observation, you have experimentation in the laboratory, and we have also theories and models. And here I'm speaking about the models in oceanography. So first, the Reynolds number. So at low velocity, Osborne Reynolds, a British researcher from the 19th century, found that, in fact, the flow is laminar, so it means it's regular. Then if you increase the velocities, you obtain the instabilities, and for large velocities, the behavior becomes turbulence. So the Reynolds number was proposed in order to quantify the turbulence. So the Reynolds number is obtained, it's a number without dimension, and it's obtained by computing U times L divided by nu. U is a characteristic velocity of the system, L is a characteristic length scale of the system, and nu is the viscosity. Its unit is square meter per second, and you can see here the typical values of viscosity in air or in water. So in fact, the viscosity depends on turbulence in water. So you can see here that, in fact, the viscosity is larger for low temperature, and it becomes less viscous for large temperatures. So we are dealing here about modeling. So modeling is done using the Navier-Stokes equation, which are used in order to describe turbulence. So here you have a compressed notation. You have 4 unknown. So 3 components of the velocity vector and the pressure. And you have 4 equations. The last one is incompressibility equation, and the first one is a vectorial equation. So you have 3 equations, in fact. If you develop this, because this is a compressed notation, if you develop it, you see that Navier-Stokes equation can be written using different partial derivatives. We also, something which is important in our case is also the fact that we have the transport of a given quantity. We call this a scalar. It's called theta here. This theta can be a concentration of a chemical product. It can be phytoplankton density. It can be salinity. It can be temperature. And so it's transported by velocity. So U here is the velocity vector. And we can see here that we have a bit simpler equation for the transport of this scalar quantity. If we develop it, we have this quantity which is shown here. And of course, this is only the dynamical part, because we can also add here on the right chemical or biological reactions. Speaking about statistics, so we have different statistical indicators. The most simpler one is the mean quantities for the velocity and for the passive scalar. And we have also second moments, meaning variance and standard deviation. So we have the variance, the scalar variance. And for the velocity, we have 3 terms. So we will have 3 variances. Variance for the x component, the y component, and the z component. If you add all 3 variants and divide by 2, you obtain something which is called the kinetic energy. We also have the dissipation of scalar variance, which is called chi. It looks like x, but it's a Greek letter. And we have epsilon, which is the dissipation of kinetic energy. So we have the exact expression here, and also the simplified expression. And globally, in fact, to characterize turbulence, we have these 3 numbers. We have the Reynolds number, we have the kinetic energy, and we have the dissipation. And in fact, we can see these numbers are like indicators of turbulence. It means if you have a given system with these different indicators, different values, for example, in the laboratory, you can compare the results that you obtain with the same numbers in the field. Or if you have two different systems in the field, you can compare them because you can use these indicators in order to compare them. So this is a very classical indicator that I use in Turbulence. Now I go to what is called direct numerical simulation. So it means that if I go back to the equation, here, we have something which is a bit complex mathematically, so it's not easy to be solved, and we don't know the exact solution. But in fact, you can approximate all partial derivatives using finite difference. And so it means that all the partial derivative will become a ratio of and difference. So in fact, you just add and divide numbers. So this can be done also for the passive scalar. And then you can do what is called the direct numerical simulation of Navier-Stokes. You do this on a grid, very fine. For example, typically the grid size will be the millimeter because you need to have to do the partial derivative at a scale which is very small. And then you can produce a very realistic simulation of turbulence. This is really time consuming, in fact, in practice. And so it can be done only recently with quite realistic simulations. Why it's time consuming? Because the computing time is proportional to the cubic power of the Reynolds number. So we can do this now for more than 50 years, but we really need very powerful computers to do it. The present time maximum value of the Reynolds number is 50,000. So what is the Reynolds number for the ocean? So if you consider a typical velocity of 1 meter per second and a typical size of 1,000 meters, the viscosity is 10 minus 6. So we can see here with the computation, we have obtained a Reynolds number which is 10 to the 9. So we can compute, here I show the example. Now we can, during 1 week computation, we have a Reynolds number of 45,000. So by considering that the computing time is proportional to the cubic power of Reynolds number, we can see that for the complete ocean, we need 200 billion years. So it means that we need more than the age of the universe to do a DNS of all the ocean. So it means it's not possible, of course, now. So why is so complex? Because in fact, to perform DNS, as I said, we need a grid size which is smaller than the Kolmogorov scale. It means smaller than about 1 millimeter. We need really a huge grid in order to do this kind of computation. But of course, we can have some models of water turbulence. So how can we do this? In fact, the solution is the fact that we increase the grid size. The typical grid size of the models for the present time is from 10 kilometers to 100 kilometers. And also if we consider local modelization in coastal seas, for example, you can have a grid size of 100 meters, for example. So it means that, in fact, you have the real dynamics of the system should be done at the millimeter scale, which is a Kolmogorov scale. But all the models are working at a grid size which is much larger. There is a ratio of about, in average, 1 million between the small size of the system and the grid size. So that's why we can have the question: can we consider the system at a large scale by doing an average of on a big grid size? What about the small scales? So we can say it in another way: the average of Navier-Stokes equation, so is that the reality, is it equal to the model of at a given grid size? So can we neglect the small scales, in other words? In fact, the solution, the answer is no, because in fact, we need to add what is written here in red. So it corresponds to small scale flux. And globally, in fact, there is a new term. It corresponds to what's happening at small scales. So in fact, the model cannot be exact if we don't take into account what's happening inside the grid. So it is this flux. So it's called the turbulence closure problem. And so it means that the models which are used right now are not exact. They're not direct numerical simulation of the system. It's an approximation which is done in order to parameterize the small scale flux. And but in fact, it's of course it's working. It's to some sense and to some limit, of course, realistic. And you can see here one example of such modelization at a global scale, and you can see many different eddies in the system. So that's all for this topic. I thank you for your attention. Here I put some of my publication in this topic. Thank you very much.